Good morning, ladies and gentlemen. Sorry for this misunderstanding. It appears that I've forgotten to post Zoom link to this session on time. Oh, there's so many things to do by the end of semester. Exam preparations, rounding off all these courses. Sorry about this. Anyway, we will proceed with a session of supervised homework. It was the last homework package consisting of two problems, 9 and 10. And as usual, I will go through homework problem, explaining what is that about, trying to pinpoint formulation. And then there will be supervised homework. So you would put the questions to the chat. You will raise your hand, and then an instructor will contact you in the chat. You will explain your question. You will get the answer. Right? Then somewhere in like 40 minutes, I will do the same with homework problem 10. And again, you will raise hands and you will be solved by the instructors. Let us see how many of you are there. Just any participants. Let me check if chat works. Let us chat. Good morning to everybody. That's very good. That's very good. So let me start explaining homework problem 9. Right. We have an electron. We have an electron, and it is confined in a quantum dot. And this quantum dot is flat. One can think of two-dimensional electron gas, where these electrons are confined. So one can safely assume that wave function is concentrated in the plane z equals 0. Right, the confinement potential is parabolic and symmetric with respect to x and y. Right, and in this case, the electron is in parabolic potential and eventually presents a realization of harmonic oscillator. Moreover, there are two harmonic oscillators. So it is a bit funny, eh? We think that electron is fermion, but we use bosonic operators to describe its state. That might sound controversial, but there's nothing bad about this. The problem that we have always a single electron in the dot. Right? So we don't apply this creation and annihilation operators of electron. Instead, we consider this electron as a sort of a field, if you wish. And this field can have bosonic excitations. All right. So never mind. The Hamiltonian is like this. Hamiltonian of electron. There's a frequency at which it oscillates, and two possible modes, two possible oscillators, X and Y. Why is it true? Because it can oscillate in X direction and in Y direction as well. Right, we also need operators of coordinates and operators of coordinate in X and Y direction. And that's how they are expressed in terms of corresponding bosonic operators. Good. R is given. R is a constant. It comes from parabolic potential. Then we kind of go to usual setup, which we utilize when we talk about the atoms. The coupling of the electron and the electromagnetic field is taken in dipole approximation. Somebody's calling me. Is it related to education? Oh yeah. That was Richter. But Richter is here, as far as I understand. Richter is already in trouble. He doesn't wait. Anyway, let me write him. Right, so we consider the coupling in dipole approximation. Good. There's a component of dipole moment in X direction, Y direction, and they're coupled to corresponding electric fields, which are operators. In terms of the bosons. It's very much like we did discussing the emission from the atom. And in fact, we have an atom, artificial atom, a little bit funny one, an atom in parabolic potential. Good, so we have photons describing the field. That's ugly coefficient as we discussed. Yeah, this is epsilon naught. Good, and the Hamiltonian of the photons. Right. So first we would like to compute the transition rate using Fermi-Golden rule formula. So again, it's mostly an exercise in computing transition rates with Fermi-Golden rule formula. Here it is. So yeah, we need to get emissions, so we need to energize And what is this? We get it to the first excited state. We prepare it somehow. The point that this state is degenerate. Yeah? It's just a symmetry between X and Y. So there are multiple ways to prepare the electron in the first excited state. And we prepare it in this way. So we start from ground state and apply a linear combination of these two operators with coefficients A and B. Could be any complex numbers. We take them real. Good. Problem A. Sorry, point A of the problem. As usual, it is easy. It just requires you to think about this in terms of the states involved. Right. The question is a bit trivial, so initial state is given. The final state is an electron in the ground state, and there's a photon with momentum k flying somewhere. The energy the energy of excited and the resulting state must be the same, as it always do when we talk about transitions. That's why there's only one possible final state. Sorry, the final state is only of a single type. Is one photon flowing. Different final states differ by the wave vector of this photon. All right. Why energy conservation is important? If you just work with this Hamiltonian, this initial state, you can have also an excited, yet more excited states. But yeah, that doesn't happen. Right. Then one needs to compute, let's go to point B, calculate the transition matrix elements and express the rate in terms of the sum over discrete K and A. Again, we take the state with certain K, we compute matrix elements of this operator and the operator X, this and this. One has to compute the sum of two dipole moments. And that will give you transition matrix element, which has to be squared. This comes for a certain K. And in transition rate, we have to sum up actually over all possible Ks, over all possible wave vectors of emitted photon. Right, then elaboration on this expression. So we go from summation over K to integration over modulus K, right? And like in that terms, we compute the emission rate in a given direction and for a given polarization direction. Good. You are invited to use the following notations, which, as you can see, just components of these three vectors in spherical coordinates. This is propagation vector in spherical coordinates, and we arrange two perpendicular vectors corresponding to you have another version of the homework exercises than the one that is put on bright space. Really? Let me check. I don't think it was crucial. Let me try to find bright space version. Let's see. Core documents, homework. All right, so it's a bit different separation between the points. I don't think it matter much. So let me just stick to the file I have. All right, I guess it was just too many points for homework. That's why we have united the first 2 points together. Okay, right. So now we need to analyze the results. Basically, having the answer is a problem. We need to find zero intensity for polarization 1, zero intensity for polarization 2, and zero total emission intensity. Right, so this is emission to a certain direction. Right, that is different from atom because the dot is flat. So dipole moment only in x or y direction. Right, it will also depend on this constants on the preparation of initial state A and B. Good, but well, we need to obtain the total rate. When obtaining the total rate, please take into account the fact that a squared plus b squared is 1, that the state is normalized. Good. Then there's a turn in this problem, and this turn eventually has been once described by Kars, who made presentation about emission of an oscillator derived from Fermi-Golden drill. So there is a bit of twist of this exercise into this side. Right. So we add external force to the electron. And then we eventually look at the effect of this force. We derive Heisenberg equations for the operators involved. So the operators xy, and also not to forget operators of photons. So there is a big system of equations for all operators involved. All right. Fortunately, the problem is such that the resulting equations are all linear, and linear equations are easy to solve. We did it several times, for instance, when we discuss damped oscillators in the lectures. So we can solve it. We can basically exclude from the equation all operators related to photons and come to this equation given by G. Right. If there is no interaction with photons, this function, capital G of omega, would be 0. This describes the contribution of photons, and it can be seen that, in fact, this relation defines susceptibility of the oscillator, right? The coefficient between reaction x on the force in x direction. So we compute this susceptibility with taking emission into account, right? It will describe dissipation in the resulting oscillator. Good. Anyway, there is note. This note indeed is not to kind of intimidate you. It is to make your life easier, since applied force x in the x direction, one can disregard all terms containing operators y, and that simplifies the equation. In principle, I could also add force in a y direction, but yeah, let's not talk about this. Good, useful formulas, Heisenberg equation, and something about transition from summation to integration. I do believe here that you have learned already this formula, but well, never hurts to remind. And something about integration, how you integrate different things coming in your work. We keep it because, yeah, in the exam, we usually give mathematical formulas like this because it's not an exam, not an exam in math, it's exam in advanced quantum mechanics. Good, so I am done with explaining the formulation. So are there any questions about the formulation? Fine, I guess that means that everybody understands the formulation. So let us change the activities. So me Cos, Christo are present today. Raise your hands and you'll be contacted by one of us, and it will all go good. Right, I will contact Nicholas. Perhaps I need to stop. I don't have to stop, sure, but I would like. Good. This is me again. So let's talk about problem 10, last problem. It's about the laser. Since we touched laser in quantum mechanics, there will be a problem about this, but this problem, I'd say, is rather classical. So we consider a simple model of laser presented in the book 9.7. We'll have atoms that are pumped to excited state with a rate r. So this is given. And decay naturally to the ground state with a rate gamma, right? But as we discussed for laser, it's important there's a mode is very where the photons can be accumulated. Right. And in the lectures, we just considered a single mode of this kind, which also kind of can be made practical for lasers. But for this problem, we look at something more complex. We consider many modes, right? So how does it come about? The laser is in fact like Fabry-Perot interferometer. There are two mirrors, and the light goes on between the mirrors. So eventually, if you remember Fabry-Perot interferometer, this will give you a set of equidistant modes, right? And so we have integer number m to number the modes. Good. And the point which we have to take into account is the dependence of the emission rate to a given mode from m. As you see, it has a maximum for a mode at 0, and upon increasing m, it goes down. Right, it has been assumed that k is smaller than 1. Let me explain perhaps a mathematical peculiarity which also comes into play. And yeah, actually many students have problems with it. which comes to the play into the play in point D. Let us look at this expression. M is discrete, right? And if K is smaller than 1, it means that, for instance, contribution of the mode is 0 and contribution of the mode is with 1 is almost the same about mode 2, 3, and so on, till the number of modes approaches 1 over kappa. All right. So if kappa is much more than 1, this is a smooth function of M. If it's otherwise, then the maximal rate is at 0M. At M equals 1, it drops already significantly. So one cannot regard gamma as a smooth function of M. So let us understand it as a condition for this function to be smooth function of M. I don't know, kind of talking philosophically, the mass at university level is kind of almost the same for the last 50 years at least, perhaps even 70 years. But students kind of regard it differently. So I've seen many students who have a problem understanding this. If anybody of you now has this problem, please don't hesitate. Try to formulate the question. I can talk more about this. This is important. Don't see the question, which for me means that you still hesitate. Anyway, let's go on. Right, all these modes have approximately the same frequency and the same quality factor, which is natural because you're in fabric error, you're somewhere at in the limit of certain frequency. So all these modes are in fact very much close to each other, have the same quality factor. Good. Then we need to derive an equation for the average number of photons in each mode M. Right. I don't want to look at PDF files to find this equation. That was also in the lecture. Let me just reason what kind of equation it has to be. We consider equilibrium of photons in each mode, right? So there is excitation of this mode coming from excited atoms. And there is dissipation, there's damping of electrons with the rate which is proportional to inverse quality factor. The worse is quality factor, the faster the photons are lost. right? And with this, we can write an equation for excited number of excited particles, right? Just to look at all processes which would counter excitation of atoms. Those is natural decay rate and decay rate associated with this gamma. All right. Then we need to combine these two equations to actually solve for the laser. To solve for the laser state, which is in this case is this parameter A, number of excited atoms in comparison with the total sorry, the maximum excited maximum or number of excited atoms, which we have derived in the previous point. Right, so we rescale the rate, which is given because small r is given. This is also can be derived from here. And we rescale this. And there is a suggestion to represent the equation in this form. All right. Important is to get expression for xm. And let us see, I don't think I remember concrete expressions. Let me just say that this expression for xm would be rather similar to this expression. But if I remember correctly, and there will be 1 minus a here, or something similar. All right. I believe that somebody has derived already equations for xm. Perhaps Nicholas. Right. So anyway, at this form, we still have a summation. Yeah, Nicholas confirms that it is similar to what I just said. So we still have an equation which requires summation over m, and it cannot be analytically done for general case, right? So in order to solve this equation, we first need to simplify it. And in point D, the way to simplify has been proposed. Namely, we assume that we can replace summation over m by integration. And again, there is a kind of a bit stumbling point for certain parts. Well, eventually for a significant part of the students when it is valid. Let me get back to this expression. In the answer, you'll have similar question. This expression is a smooth function of m and can be integrated over m. One can replace summation by integration if this is a smooth function over of m. If it doesn't change much, if m is changed by 1, by 2, right? So this is gives you certain relation between 1 minus a and kappa. Right. We need to know this relation because we did something and we want to know when it is justified. Good. So that requires that we make an assumption about possible values of a. In fact, a should be close to 1. Right, and good. Then we again, in order to solve this equation, one has to simplify it, and simplification is achieved when we replace summation by integration and make integral. And the resulting equation can be solved in this limit, right? If we got A, we can find already laser power. Fine. There is also a bonus point. Yeah, but it is again bonus, and in order to solve it, one needs to look into the lectures, recall what is the coherence time, how it is defined, and understand how it is realized under current conditions. Good. So I believe I explained the problem. If there are no questions, I don't see questions. Then let us switch to usual activities. So please raise your hands. And I guess I will stop recording now.